Jai Hind to all. In this video lecture, we are going to discuss the duality principles and various inference rule in DSTL. Okay. So, myself Komal Rani, Assistant Professor at Ajay Kumar Gar Engineering College. So, let's start. Duality theorem. So, duality principle states that for any true statement, the dual statement obtained. Okay. By interchanging unions and intersections and vice versa, and the interchanging universal set into null set and vice versa. So, if a dual of any statement is the statement itself, nothing but statement itself. So, if the statement is dual of itself, then we said that this is a self dual. So, what's duality principle states that if we interchanging union and the intersection, so what we get is known as the duality theorem. So, basically duality principle states that if we will convert intersection to union, union to intersection, or if we convert universal set to null set and null set to universal set. Okay. So, for any true statement, if statements are true, the dual statement obtained by interchanging union into intersection and intersection into union, or interchanging universal set into null set and the null set into the universal set. So, what we get? We get the dual of that statement. Okay. So, for that must be true, for any statement that must be true. If any statement is true, if we convert union into intersection and intersection convert into union, we get the dual of that statement. That's why we call as the duality principle. So, there are two types of normal forms present here. Okay, from where we can convert any proposition into two normal form. The first form is the conjunctive normal form and the second form is the disjunctive normal form. So, let's explore about the duality principles more. Okay. So, conjunctive normal forms a compound statement. Okay. So, that is made up of the more than two statement. Okay. So, that's why we will say that this is a compound statement. A compound statement is in conjunctive normal form if it obtained by operating AND. So, this is for the AND. Okay. By operating AND among variables. Okay. So, it can be negations. So, there can be a negative A. Okay. There can be negation and connected with ORs. So, here you can see that these are the OR statement which are connected by the AND statement. So, now it become a compound statement. So, in terms of set operations, it is a compound statement obtained by intersection among variable connected with the union. So, nothing. So, here we have taken another example, another compound statement. The two variables are connected with the or we can say that the union. When combined this two statement with the intersection, we got the conjunctive normal form. So, basically here this represent the conjunction. Okay. So, here this represent the conjunction. So, next is the disjunction. So, disjunction symbol, that is or symbol. Okay, or union symbol you can say that. So, if we apply this to the compound statement which is AND operated. Okay. So, similar, a compound statement is in disjunctive normal form if it obtained by OR operating OR. So, here we operating OR among variables. So, negations again can be included. Here can be negative A, can be negative B, connected with AND. Okay. So, here these variables are connected with AND value. So, in terms of set operation, it is a compound statement obtained by union among variable connected with the intersection. So, in the form of set you can write here. So, compound statement, okay, obtained by union among variable which is connected to the intersection to each other. Okay. So, firstly we discuss duality theorem. So, duality theorem statement which is true, we can convert intersection to the union and union to the intersections. The both statement we got after interchanging, we got the dual of that statement. Okay, so duality statement is of two type, conjunctive normal form and the disjunctive normal form. Conjunctive normal form means conjunction of the disjunction values. Okay, or we can say that intersection of this union statement. And the disjunction form, disjunctive normal form says that disjunction of the conjunctions value. Okay, or we can say that union of this intersection operation. So let's discuss precedence of the logical operator. So here we have many operators. We have negation operator, we have conjunction, disjunction, implications, and the biconditional. So conjunction and disjunction sometimes, which is very much similar, very much operative to similar like the and or operator. Okay, so what are the precedents to solve any statement? So first precedence will give to the negative. If in any statement negation is there, so we have to solve the negation. The second is the conjunction, or we can say that the and operator. The third is the disjunction, or we can say that the or operator. Okay, fourth one is the implication operation, and the fifth precedence goes to the biconditional operation. So for example, we have taken P implies Q conjunction negation of P. So first precedence is negation, so we have to solve this negative. Okay, so if let us consider P is true initially and Q is false, so what we get, P implies Q implies negation of P, so that is equal to P is true. Okay, true implies false disjunction false, and false disjunction false gives you the false, or true imply false which gives you the false value. Okay, so you can solve this statement with the help of the table, truth table also. Okay, so problems. So let's discuss one problem. Construct the truth table for the compound proposition below. So here we have given some statement. Okay, so we have to build some proposition logic. So let's start with P implies Q, because we have here the two variables. So four possibilities are there. So we have initially taken the P true true false false and the Q true false true false. Then here we have to find the negation of P, okay, and the negation of Q. So just we do the negation of P, true will become false and false will become true, and then we will solve the negation of Q. And then R, here R is nothing but the this statement. Okay, so R is not a third variable. The combined statement we write, that is the R. Okay, so you can write here negation of Q, disjunction, conjunction, negation of P. So whole statement solve, when you solve we get this. Okay, and then P implies this. So P implies this, true false will become false, true false will become false, false false become true, false false become true. Okay, the only condition P implies Q false condition is that the P is true and the Q is false, the result will be false. Other than all statement, okay, FT is true, false false will become true, and the true true will become the true. So from that possibility we write here. Okay, and then we implies just S bidirectional negation of Q. Okay, so we write here S. What is S here? So S is not a fourth variable, it's a concrete part of that. Okay, P implies this statement is known as the S. So we here divide the statement P negation of Q, conjunction negation of P, and bidirectional negation of Q. So here we write here, this is the R, okay, and bidirectional negation of Q. So here P implies, R implies, then P implies R, the whole statement will become the S, then we find the bidirections, because we have to solve any equation step by step. So firstly, you solve this negative part, okay. So after that, you solve this implication based on that precedence rules, and at last you will solve the bidirectional, biconditional statement. So this is the way how to solve this problem or any type of these problem based on that precedence, okay. So keep in mind the precedence rule. The first is the negation, you have to solve the negation values, and then the secondly you have to solve the conjunctions operation, okay. Third, you have to solve the disjunction operation, and the fourth you have to solve the implication, and the fifth at last you have to solve the biconditional statement. So based on precedence, any truth table, any problems you got in the similar way you can solve. So let's discuss the three types of tautology, three types of the tables, okay. So what's the result we got? So based on that result, we convert into four types, okay. So what are the proposition logics gives you the result? Based on that result, we will convert. This is a tautology, this is a contradiction, this is a contingency, and this is a satisfiability. So let's discuss one by one. So what is tautology? So for any two variable, if the result will give you true in any condition, then we say that this is a tautology. So a compound statement which is always true. So here we have taken only one variable. So we will got two possibility, true false and false true. If we got the two variable, we will got the four possibility, okay. So here you can see that in any condition, so with here the two possible conditions are there. So for two possible conditions, the result will be true, always true. Then this types of tautology, this type of proposition is known as tautology. The second is the contradiction. So compound proposition which is always false. In any particular condition, the result is always false. So we can say that this is a contradiction. So compound proposition which is always false, we can say that this is a contradiction. And the next one is the contingency. Compound proposition which is sometimes true and the sometimes false, okay, that we got the mixed of the true and false, then we can say that this is a contingency propositions, okay. And the satisfiability, a compound proposition is satisfiable if there is at least one true result in its truth table. So at least one, more than one can be there. So at least one true. If all true, that is tautology. If all false, that is the contradiction. So if contingency, that is the mixed of that. So for satisfactory, at least one are true. So unsatisfactorily, not even a single true result in a truth table. So you can say that contingencies is always a satisfiability. Why? Because contingency contain the mixed of the true and the false. So contingency is the satisfiability, and unsatisfiability is also called as a contradiction, where not even a single true result in a truth table. So there are two statement. We can say that the valid statement or invalid statement. So valid statement, a compound proposition is valid when it is tautology. So valid means always true, or invalid is if there is either a contradiction, that is always false, or contingency, that is it is a mixture of true and false. So we can say that this statement is an invalid statement. We can't reach at the conclusion what will be, it's true or it's false, okay. So these types of statement are known as the invalid, and the valid statement is that statement which is always true in any circumstances, okay, in any situation. And invalid statement which is a mixture, or which we can say that this is a biased conditions, okay. So biased condition where we can't reach at the conclusion, so we can say that this is a invalid statement. So let's discuss the logical equivalence. Compound propositions P and Q are said to be logically equivalent if P biconditional Q is tautology. Okay, so logical equivalence is denoted by either this symbol or this symbol. So for logical equivalence, you have to find this P implies biconditional Q is tautology. If it is a tautology, then we can say that this is a logical equivalence. Or you can say that if there is two statement and two statement got the same result, then these two statements always a logical equivalent. Okay, with same condition it will give the same result, true, and the same condition, similar conditions, it will gives the false value. So two compound statement can be logical equivalent in that case. Okay, so to have to prove the compound statement is logically equivalent or not, we have to follow some logical equivalence rules, or we can say that logical equivalence laws. So based on that law, we prove that these two statements are equivalent or not equivalent. Okay, so here P disjunction T is logical equivalent to P, because so whatever be the value of P, true doesn't affect that value, because we are doing this disjunction, conjunction here. Okay, conjunction, we can say that the intersection. So intersection here will gives you the false, will give you the false value, true will give you the true value. Okay, so we can say that these two statements are logically equivalent. Okay, so because this true doesn't affect the result. Okay, so here P statement result is similar to this statement, so we can say that these two statements are logically equivalent. So what are the basically logical equivalence law to solve these types of equivalence? So let's discuss. The first is the identity law. So here you see that this is the identity law. That means if you are doing the conjunction, so whatever be the value of P, the result will be that. And whenever you will doing this disjunction value, so whatever be the value of false P, the result is always P. Okay, here false doesn't affect the value of P, here true doesn't affect the value of P. So these two statements are logically equivalent. Next is domination law. So domination law means when something is dominated. Okay, so whenever you are doing this disjunction, so whatever be the value of P doesn't affect the statement, it will always gives a true. Okay, like this here P have two possibility, true and the false, and true is always true. So P disjunction true will always gives you the true value, because we are doing the disjunction. So similar way, the P value doesn't affect when you are doing this conjunction with the false, so it will always gives you the false value. The third one is the idempotent law. Okay, idempotent means operation to itself. So P disjunction P will logical equivalent to P, and P conjunction P is logical equivalent to the P itself. Next is the double negation. So negation of negation. So suppose P is true. Okay, so negation of P is equal to false, and negation of P, that is equal to again true. Okay, so this is the double negation law, which is not, which is these two statements are logically equivalent. Commutative law says that, so whatever be the operation between that, okay, it's if it is disjunction and disjunction. Okay, so P disjunction Q or Q disjunction P always gives you the same result. Similarly, P conjunction Q and Q conjunction P always gives you the same result. The next is associative law. P disjunction Q disjunction R. So similarly, associative law if you follow, there will be the same result. Thus, these two statements are always equal in nature. Next, again, distributed law. Distributed law says that these two operations must be different. Okay, if you will use here disjunction, inside there must be a conjunction. Okay, so when you solve, these two statements are always equal. So next is the De Morgan's law. De Morgan's law says that if the negation of whole thing, okay, P conjunction Q, that is logically equal to negation of P disjunction negation of Q. Similar way you can solve this. Okay, absorption's law. So P disjunction P conjunction Q always gives you the P. So these law can be verified with the help of the truth table. You can solve with the help of the truth table. Okay, so when in a paper you have to set that these are logically equivalent or not, so you have to follow these law. Okay, so based on these law, you have to prove that this is logical equivalent or not. Simultaneously, you can make the truth tables to prove that. Next is the negation law. P disjunction negation of P will gives you true. P conjunction negation of P will gives you the false value. So these are the various law to prove directly without the help of the truth table that these are logically equivalent or not. So here some examples are there. Logically equivalent involving conditional statement. Okay, so here first example you can see that P implies Q, which is logically equivalent to negation of P and disjunction and Q. Okay, so initially we have taken the P value is the false and the Q value is the true. Okay, so that's here P is false implies this Q. Okay, and the negation of P false. So when you solve this, true imply false. So true imply false is equal to false here, and negation of P, that is equal to true. Okay, so because we have taken initially P is equal to false and negation of P is equal to true. So true disjunction false, that is equal to false. Okay, so false here gives you the false value. So you can consider any value. Okay, you can consider any value. So based on that you can taken the P is true or Q is true. Okay, or P is false. So so P and Q are two variables, so 4 conditions are there. So based on that 4 condition you initially take any value. Okay, so because logical equivalence are that is tautology, for any P and Q the value should be same. Okay, left statement should be right statement. So based on that you can say that. So you can take here P is equal to true and the Q is equal to false. Okay, so or you can take that P is equal to false and Q is equal to true. You can take both false, you can take both true. Okay, so let's discuss the first. P implies Q, which is equivalent to negation of P and Q. Okay, so here we have taken P is equal to true and the Q is equal to false. So P is equal to true and the implies Q is equal to false, which is equivalent to negation of P, that is equal to false, and this is equal to false. So here what's this formula says that which is very much equivalent to negation of P. So true implies false, that will gives you the result false. That is the only condition of the false, which is equivalent to false. Okay, so because we have taken Q as a false, so this false will equivalent to false. So based on that value you can say that these are logically equivalent. So based on that there are some examples are there. So you can solve these examples based on the propositions. Okay, and you will tell initially you have taken any condition for P and Q and start solving these questions. Okay. So here logical equivalence involving biconditionals are there again. So let's discuss this one problem here. So biconditional says that negation of P biconditional negation of Q. Okay. So what's when you solve this? So this is the P implies Q and Q implies P. This is the expansion of P biconditional Q. Okay. And P P implies Q conjunction disjunction Q implies P. So which is logically equivalent to negation of Q and negation of P. So if you change that, okay. So if we change that, negation of P and the negation of Q. So here you have taken negation of P S and negation of Q is R. Okay. So when you prove that here S implies R and R implies S, that is equal to S double implications biconditional R, or we can say that this is S is nothing but the negation of P and the negation of Q. So similarly you can use this statement to solve any logical precedence or equivalence. Okay. So here some problems we got. P and Q are true proposition. Which of the following logical expression is equivalent or not? So you have to solve. So here we have taken the four statement. So you have to check these are the true or false. So we have taken initially P value is equal to true and Q value is equal to false. As we discussed, you can take any value. Okay, first statement will gives you the result P negation of Q, that is equal to true and that is true. That will give you the true value. For second condition, negation of P and disjunction Q, that is equal to negation of P, that is equal to false and Q is equal to false. So false will give you false and this negation will give you the true. Okay. And the third condition is P disjunction Q conjunction P disjunction negation of Q and negation of P disjunction negation of Q. So here P is equal to true and this is false and this is P true and this is true. Okay, and this is false and this is true. So this will give you the false value, this will give you the true value and this will give the false value. So ultimately we got the result, the true value. So these three are equal. Okay, and the fourth one is the, here we can consider P. So directly we can say that P true and false, true and false, that is true and false. So we got here true and false, that will gives you the false value. Okay, true and this will become the true value which will give the true value and this will gives you the false value. So false disjunction true disjunction false, that will gives you the true value. So in all the four cases you will got the true value. So you can say that all of these are logically equivalent. This is the example of question from the GATE 2008. This is very much simple. Okay, so this is the one way to check, or this is the other way to check based on that propositions. Is it logical equivalent or not? Okay, so I can explain that there is a two method. The first method is the based on the proposition true and false or a truth table, and the other thing is that based on that proposition's logic, okay, as we discuss various laws, okay, and then you will solve directly without this true false values. And the second one is the okay, so this is the way you can use that. So this is the way how you can solve the proposition logical equivalent or not. So let's discuss. Initially we discuss the duality principle. Duality principles will convert the, if for any true statement duals can be obtained by interchanging intersection to union and the union to intersection, okay, universal set to the empty set and empty set to the universal set. Next is conjunctive normal form, okay. So conjunctive means the two statement which are or operator or union is combined with that intersection, okay, or we can say that the conjunction. Disjunction, when two or more statement are combined with that disjunctive, okay. So here we discuss some precedence rule. Negation will go to the first precedent, conjunction will go to the second precedence, and the disjunction will go to the third principle precedence, and the fourth is the implication, and the fifth one is the by condition. So this is the way how to solve the truth table, okay. Now there are fourth type of table. We can say that tautology, contradiction, contingency, and the two statement satisfiability and unsatisfiability. Satisfiability means at least one is true in the result, and unsatisfiability not even a single true exists. That will indirectly show that this is a contradiction in nature, okay. So valid statement is that statement which is always true, or invalid statement is that statement which is either true or false, or we can say that which is either contradiction in nature or contingency in nature, okay. So these are the logical equivalence. This is the various law, based on that you find this is logical equivalent or not, okay. So these are the various methods to solve these logical equivalence, okay. So here we solve one question from the gate, how to solve, okay, with the help of tautology, with the help of the different rule in the form of true and false, or based on the that rule, okay. So here in we convert this conjunction with dot operator, okay, or we can say and operator, and with the help of this or operator, then we apply here this distribution law, p common q plus q dash, okay, or so this is always a true value gives you, and this again we apply the distribution law, okay. So this will again gives you true value, so this will give you p plus q, or we or operator will be, which is very much equivalent to the conjunction, okay, disjunction. So similar way you can use here. So firstly you will convert this operation, okay, conjunction will with or and disjunction with the and based on the various law, distribution law, okay. So here we apply the distribution law, which is always true. Here again we apply the distribution law, so which is very much equivalent, okay. So this is the, thank you so much. If hope so you will like the video. Thank you so much.